Great, welcome back. So now it's part 2 of Rohit's tutorial on identification.
All right. Okay. So we ended on the note of the Boark graph is not identified. I was asked a very good question about where is all this going. I guess I should point out all of this stuff eventually kind of leads up to the ID algorithm, which is it's a sound and complete algorithm in the sense that you give it an ADMG that's defined over the observed data variables, and then it outputs an answer. You can have one of two answers. It can either say that your query is not identified, or it can say that your query is identified and give you a functional corresponding to the identified functional. And so, in 2006, Ilya and some others at Huang and Valtorta spent some time thinking about this completeness argument for saying that when the do calculus or equivalently the ID algorithm tells you something is not identified, how do you actually prove that something is not identified? And so this is one way of doing it. And just as a recap, so this is a comparison to the older proof, and generalizations of this proof is basically what have been used to prove the completeness of the ID algorithm, but it produces one counterexample as opposed to a set of counterexamples that's based off of this technique. Okay, so that's where we're headed. Is you specify an ADMG, and it should give you an answer. And if it doesn't give you an answer, we should know why it's not giving you an answer. Okay, so as I mentioned, so the Boark shows that unmeasured confounding can be a problem. So if I just have unmeasured confounding between my treatment and one of the potential outcomes, it turns out to be sufficient to show that things are not identified. But it turns out that unmeasured confounding isn't always a problem if you have additional information in your data. So one very, very classic example of non-parametric identification despite unmeasured confounding is what's known as the front door model. And now the front door model is most typically represented as this ADMG over here. It's equivalent to saying that actually there's just an unmeasured variable, u, that points to both a and y. I can draw that edge. No, it won't let me draw that edge. All right. I'll just leave u over here to say that, okay, there is a u variable that can point to both a and y. But here is what the NPSCM IE model, so if I expand the whole thing out, put all of the potential outcomes on the graph, this is what it would look like on the left. So this would be the full data law, and this is the observed data law for the front door model. So what do we have? We have a to m to y, so the only parent of m is a, and the only parent of y is m. And then you define your one step ahead. So in this case, you have MA0, MA1. So what would have happened to M had I intervened and set A to 0 and 1? And then what would have happened to Y had I intervened and set N to 0 and M to 1? So in Pearl's description of this model, the example, so this is like building off of this morning's talk. Ronald Fisher was maybe shilling for tobacco companies, let's say. And was saying that you can't prove that smoking causes lung cancer. So Pearl tries to provide the front door model as an argument saying that despite unmeasured confounding, perhaps you could compute the causal effect. So the classic story is you've got your treatment A as smoking, M is the amount of tar that accumulates in your lungs, and then Y is whether you develop lung cancer or not. And it's actually much easier to reason about this through the assumptions through the observed data ADMG. But what it's saying is that, all right, I have unmeasured confounding between A and Y, but crucially, I don't have unmeasured confounding between A and M, and no unmeasured confounding between M and Y. So whatever that unmeasured confounder is between A and Y does not also confound the mediator. Which can be a strong assumption, And then the other big restriction here is that A causes Y only through M. And you could have multiple mediators there if you like, but in this case, I'm just generically drawing one mediator. Okay, so that's the front door model. Here's a template, the single world template, and here's how identification for the full data law, or rather the single world parameters of the full data law in the front door model would proceed. So I've got, again, I'll actually start with P of MA because MA is just, it lies in its own little, district it's called. So bidirected connected components in an ADMG are called districts. So MA lies in its own district. A and YM are in one district together. So I have two districts among the potential outcomes. The one step ahead here. Okay, so P of MA, from the graph, I can read off that MA is independent of A. And so this is just P of M given A is equal to A by independence and consistency. So that's done. And then I'll start to break these two down. So I've got P of A and YM. So this joint distribution, and I can use chain rule here to say that this is equal to P of A and P of YM given A. Oh no, I've run out of space again. Let me make this a tiny bit smaller. Okay, P of A, P of YM given A. Okay, and then by independence, so you'll notice that YM does have a path to M. I can go YM, follow this bidirected edge to A, and then follow that directed edge to M. But if I'm conditioning on A, YM is independent of M given A. Okay, so that licenses me to say that this is equal to P of A times P of Y given M is equal to M and A. Okay, so that gives me this joint distribution, and then I can start to decompose that joint. So I can say that from P of A and YM, I can get P of A. P of A is actually, it's just already an observed data quantity, so that's just identified. And then finally, I have P of YM. P of YM is just, I take this guy and then sum over all values of A. So this is just equal to a summation over all values of A. P of A is equal to little a, P of Y given M is equal to little m, and A is equal to little a. Okay, so that's identification of all of the single world parameters. Now, putting these all of these together, this is when I tell you a little bit about the nested Markov factorization. So here's what the front door, just recall, here's what the front door model looks like. Got a bidirected edge there. And then we're saying that P of M equals 0 given A equals A corresponds to this post-intervention distribution. What you'll notice is that depending on the value of A, I could get two different probabilities. Right? So if A is equal to 0, this is one quantity. If A is equal to 1, this could be a distinct quantity. So this is actually two parameters. This one over here is similar. For different values of M, I could get different post-intervention distributions where I intervene on M and calculate what happens to A and Y. So this is also two parameters. So this complex, this is sort of like a conjunction of two probabilities, but it's only input is M, really. Okay. And then this is just one parameter And then finally over here, this complex distribution that's then marginalized over, also its only input is m, so there are two different parameters over here. So overall that gives me 2, 4, 5, 7, and if you think about the number of parameters you need to specify a joint over 3 variables, that's exactly 7 parameters. So there's a one-to-one correspondence between these post-intervention distributions and something that happens to parameterize the joint on the front door model. Now, in the nested Markov paper, what they do is that they call these kernels. So this over here is the kernel of m given a, and the reason they use q is to say that they may not correspond to regular marginal distributions or regular conditional distributions. That's a kernel of q of m given a. This is a kernel of a and y given m. This is a kernel of just a, and then this is a kernel of y given m. What you can also do is associate each of these kernels with what's known as a conditional ADMG that shows you what kind of post-intervention distribution these kernels are modeling. So q of m given a, if I think about what this causal parameter is, it's asking what happens to m when I intervene on a. If I was to represent that as a conditional ADMG that says, okay, the variable a is fixed, and it just points to m. Right? And you can kind of see that you're extracting a piece of the front door model, and that's like, we're going to start composing different pieces of it. Okay, so this is one piece. This piece is what happens to a and y when I intervene on m. So that's what this looks like. Y, A, and immediately from here you can see if I was to combine these two conditional ADMGs, that forms the front door model. Right? If you just superimpose those two things on top of each other, it extracts the front door model. Okay. And then Q of A is a trivial graph. Q of A is just the node A with nothing else going on. And then finally, Q of Y given M is the graph that looks like this. We have M pointing to Y. And so these kernels correspond to what are known as intrinsic kernels in the nested Markov factorization. And then what the nested factorization will say is that if you sort of walk through all of these what are known as reachable graphs by intervening on variables, so the graphs that I'm talking about are just the graph A, this conditional ADMG my, this one A to M, this one AY, and then you have M pointing to Y, and then you have, of course, the original graph. Essentially, the constraints that are encoded in these conditional ADMGs are the constraints of the nested Markov model, and each of these graphs factorize, and the pieces of the factorization are exactly these kernels. Now, if you treat an ADMG as being the margin of a causal model, these have nice one-to-one correspondence with post-intervention distributions. But what I'll say is that the nested Markov model actually need not be causal. You could just use an ADMG as just a statistical object and have no relationship to causality. But I do think the causal interpretation of these kernels is nice as being post-intervention distributions. Okay. And then one more thing is you can combine these identified parameters. So just like we were able to combine identified parameters of the conditionally ignorable model to get the front door formula, to get the G formula, you can combine these to get the front door formula. So you would first say, okay, you have P of YA. P of YA by recursive substitution is equal to P of YMA. So it's like the value that Y would take if I intervene on A and check what the value of M becomes. And then I marginalize over M. So I marginalize over all possible values of M. I get P of MA equals little m. And then Y MA equals little m. Then by consistency, this is just equal to a summation over all possible values of M. MA, oops. MA times, oh no, I've run out of room again. Let me remove this. Let's cancel that out. Okay, and we'll go here. So this is equal to sum over all possible values of M, P of MA times P of Y M. Okay. And then finally, you can see that P of MA we've already got over here, and P of YM we've already got over here. And notice that because we're intervening and setting A to some specific value, the only thing that you really need to be careful of in the front door formula is that this A that's in the second piece should be different than the A that you're setting to, because this is like a marginalization over all possible values. All right, cool. Okay, so now this kind of leads to the question of like, all right, there's maybe a bag of tricks that you could use, something like front door. And the interesting question is, when do we fail to identify single world parameters? So we know that the bow arc graph leads to non-identification. So if I have A to Y and A bidirected Y, we know that leads to non-ID. We also now know that if I have A to M to Y and A bidirected Y, that I'm actually okay because the front door model is identified. But the interesting question is, like, are there other things that prevent non-identification? There's a criterion that I specifically really like because of its simplicity. So there's a whole range of things that you could consider, right? So the simplest possible form of identification is the conditionally ignorable model, where we say, all right, we have a set of baseline covariates, conditional on which you will get this independence of A being independent of YA given C. That's kind of the simplest form of identification. Front door is a little bit more complex. And then the ID algorithm sits at the other end of complexity of like, there's a ton of setup that you need to understand before you understand the ID algorithm. But there is a very, very simple criterion. And here's what that criterion is. This is due to Tian and Pearl from 2002. So they say that the effect of a single treatment A on all other variables on the graph, so basically the post-intervention distribution where you're looking at the effect of A on all other variables, is identified if and only if there is no bidirected path from A to any of its children in the observed data ADMG. Should also clarify that this is a criterion that was originally defined on the observed data ADMG. So it's a really simple criterion. It's very easy to state. It covers many popular models. So the conditionally ignorable model, there are no bidirected edges, so it definitely satisfies this criterion. The front door graph satisfies this criterion because there is a bidirected edge, but not to a direct child. So you're okay in the front door graph as well. And so you could expand this graph out make it a lot larger, but as long as your treatment does not have bidirected edges to any of its direct children, it turns out that you're completely fine. And in fact, the identification formula looks almost exactly like front door, just with a few variables added. So you get multiple conditional probabilities over here, and then multiple conditionals over here, but otherwise it's roughly the same. Okay. And then the other reason I like it is because estimation under this criterion is also well studied. The reason it's well studied is because when you have full law identification in this way, you sort of don't have to worry about the non-identified pieces, and you just say that, okay, I'm going to estimate pretty much everything, and we know how to estimate this class of effects in this class of models pretty well. Okay. So here's an example of a graph that doesn't satisfy this criterion. Okay, so this is the simplest example of a graph that doesn't satisfy this criterion. I have A to Y, and then C bidirected A, C bidirected Y. You can see that A does have a bidirected path to its child, so we're not identified. This is kind of an interesting example. So if you look at the full data law, this is what it would look like. So I have a bidirected edge from C to this potential outcome, bidirected edge from C to the other one. And there is only one set of one-step aheads because I only have A to Y. There's no other potential outcomes involved here. Okay. But the interesting thing about this is that according to Tian and Pearl's theorem, P of C and YA is not ID. That doesn't, however, necessarily mean that P of YA is not ID. It could be that you can just get the margin, but you can't get the joint. And this is actually the simplest example in which you don't get that joint, but you do get the margin. And the reason you get the margin is because these are all bidirected edges. So you can actually see that YA is marginally independent of A. So I just have a bidirected path to C, to A, and so I just have a marginal independence between these two. Okay. And because I have that, I can say that P of YA is just equal to P of Y. It's just equal to P of Y given A equals A. All right, but it's kind of interesting to see the again, the argument for why things aren't identified here. So you could play the same game. I'm going to make this model as simple as possible. I'm going to add or go to a submodel where I don't have the extra edges from C to YA1, and I also don't have the cross-world edges. One interesting thing to note here is that the observed data distribution is actually a little bit weird in this case. So it turns out that I have P of C equals 0, which is one parameter. I would have P of A given C is equal to little c. So this is 1, this is 2. But because I have a bidirected edge in just one of these, to one of these potential outcomes but not the other, it turns out that P of Y given A, so this conditional distribution is a little bit weird. So when A is equal to 1, that means Y is deterministically equal to YA1. And so it's not a function of C. So you can see that YA1 is completely independent from C. So this actually decomposes into two pieces where I have Y given A is equal to 1, which is 2 parameters, and Y given A is equal to 0. This is 1 parameter, and Y given A is equal to 0 and C is equal to C, that's 2 parameters. Okay. All right. So in total, the observed data has 3 and 3, so it has 6 parameters. Okay. Now if we look at the full data law, we've got P of YA1. We know that this guy is fine. That's just ID because it's sitting out here alone. And by marginal independence, we can identify it. Now, the Mobius parameterization, remember the way that it works is you do all univariate margins, then you do all bivariate margins, and then you do all triplet margins. So, if I list all of those out, here's how it goes. So I've got P of YA0, which is ID, P of C, which is ID, P of A, which is ID. And to not be sloppy, these are all, with respect to some reference value, just all of them being equal to 0. Okay, so I have 4 things that are identified so far, and remember I only have 6 in my observed data distribution. So I'm getting awfully close to proving that this joint may not be identified. Okay, so what are my other Mobius parameters? I have P of A equals 0 and C equals 0. That's a bivariate margin. I have P of C equals 0 and YA0 equals 0. That's another bivariate margin. And then I have my final triplet, which is A equals 0, C equals 0, and YA0 equals 0. So this is just observed data. That's identified. By consistency, this is identified. And so that necessarily means that this guy is not ID. So that joint is not identified. Okay. I'll pause for questions for a sec here. Yes?
Yeah, I'm not sure if it's purely terminology, but how can we still be identifying only single word parameters if we are imposing a confounding structure that is different for YA0 and YA1? Like here we said,
Oh yeah, so I'm just moving to a submodel. So this is just for convenience of the proof. So I could do the proof with these additional edges, but I'd have to list more Mobius parameters, some of which are cross-wall parameters. Cross-wall parameters we know for sure are not identified. So I'm moving to a simpler model where I say, all right, let's remove those cross-wall parameters and show you that despite having removed those cross-wall restrictions, I still don't get identification of a single world parameter. And you had a question too? Yeah. Yes. Okay, so identification is about getting a bijection. And so the observed data only has 6 parameters that I can use for information. And in the full data law, what I've shown is that 1, 2, 3, 4, 5, and 6 are identified. So if I was to identify a 7th, that would mean that I'm doing something fishy over here. Basically, this is my degree of freedom that once I specify all of these, this can take on whatever value as long as it gives a valid joint distribution. Yeah. Okay. All right. So you can you can apply the Mobius parameterization. You show that this is not ID. So I will say there are some caveats to this proof technique. So you have to have a parameterization that captures all the quality constraints. There's been a lot of, as I said, a lot of the groundwork has been laid for us conveniently enough. So it turns out the nested Mobius parameterization does capture all the quality constraints in at least the binary case, and when your unmeasured confounders are unrestricted. Okay, another fun fact that I'll point out here is that this actually unifies a completeness proof in causal inference and missing data. There are interesting connections between causal and missing data, as we all know. So this same structure of having a bidirected path to one of your children in the observed data ADMG is essentially the exact same criterion that leads to non-identification of the full law in missing data. Now, in causal, we have 2 counterfactuals, or at least 2 counterfactuals if you're dealing with binary data. What happens if you receive treatment? What happens if you don't receive treatment? In missing data, you have only one counterfactual. So over here we have yr1, which is the value of y had r been equal to 1. And the semantics of missing data graph are that when r is equal to 1, y is of course equal to yr1, so the value of y had you been able to observe it. And then when r is equal to 0, y is equal to question mark, meaning that it's missing, and it's deterministically equal to question mark. So despite all of the similarities between causal and missing data, so it turned out to be some sort of, I'd say we got lucky in the sense that the completeness result for causal and missing data in this particular scenario ended up being the same. However, there are many other problems, which include like getting just the marginals. So in this case, as I mentioned, you get P of YA over here. Here also you get P of YR1. So it turns out if all you're interested in is in marginals, missing data is much, much harder than causal inference. And I can say that because we've tried for 6 years, I think, now, and we don't have a complete theory about identification and non-identification in missing data. And that happens purely because of this difference between causal having two counterfactuals, two versions of the counterfactual, missing data having one. Yeah?
So something's confusing me about this game you're playing. So you want a dense set of counterexamples, so fair enough.
Yeah.
And you're going to use Mobius parameterization to get this dense set.
Yeah.
Not just figuring out what's not identified. Also fair enough.
Yeah.
But we all know that nested Markov model doesn't have to include hidden variable tags. In other words, I could construct a valid nested Mobius parameterization such that there is no DAG for it because it violates some inequality somewhere, right?
Right.
Okay, but causal models are hidden variable tags.
Yes.
Unless we want to get into some controversies here.
Sure.
So do you have like a way of enumerating what the actual dense set actually is? Because you can't just say, oh, anything like any valid like marginal parameter that's consistent with these other parameters that I know, like is a counterexample, because you don't know if that's a DAG or not necessarily. You also have to check that.
Well,
and that check is complicated by the fact that it's not so easy to tell what the inequalities actually are in an arbitrary DAG.
Yeah. Although,
so we have anything to say about that.
Yeah. Okay. So I would say this causal model is. Well, it is a controversial statement that causal models are DAGs. I think like this is not a. I mean, like when you actually draw out the full data graph, it's not a DAG. It turns out, right? Like because of all the restrictions of either NPSCMIE or Fristig, I think the DAG ship has sailed, unfortunately. Like we are. Well, your observed data could be a DAG, but I think your full law is.
I think. Okay, so I know that there are people in the room who wrote about this, but yeah, okay. So we can talk offline about it.
Yeah. Okay. All right. Other questions. Okay, I'll do one more example, and then I'll talk about Verma constraints for a little bit, and then we can wrap up. Okay, so this is the napkin graph. I think the story behind why it's called a napkin graph is because Elias Barenboim, who's one of Uda Pearl's students, showed him this graph, this one actually, on a napkin. He drew it on a napkin and asked Pearl, is the effect of A on Y identified in this graph? And I wouldn't be telling you about this graph if it weren't. Actually, maybe I would. I have talked a lot about non-identification, but it turns out it is identified. What you'll notice is that it does have a bidirected path from A to Y. However, you do end up with identification. You can either look at this from the lens of applying the ID algorithm. The ID algorithm would directly give you what that functional is. But I'll give you some intuition on why the effect of A on Y in this graph turns out to be identified. I don't quite know of a good story behind why you might believe this graph in a real applied application, or sorry, a real application, except for the fact that I think what I would call this is kind of a double ID model that results in non-parametric identification. You can think of Z and X as being two IDs in a sense, but weird IVs, like x is maybe a true IV in the sense that x has nothing to do with y except through a. And then z is an IV in the sense that it's correlated with a, but it also has some direct relationship with y. And actually, it's really its sole purpose is to kind of protect x, which is our like real IV. So maybe it's like IV with like a guard to give you non-parametric identification or something. So maybe in fact I should have flipped the labels. Yeah.
It's also the front door graph said XA.
That's right. Yeah. So so if you look at the margin on z, x, and a, if you just ignore y for a second, if you just look at the margin on z, x, and a, that is front door. That is exactly the front door graph, and it's actually not coincidence. You know, you do compose some front door pieces in order to get the final identifying functional in this graph.
You know, you don't have to ignore y for it to be front door. It's just front door. It's a front door graph.
Oh, yeah, it's easier to see it. Okay. So here's the argument for why you get identification of the effect of A on Y in this graph. This is the simplest example of one where a non-parametric identifying functional is actually a ratio of things rather than just being a straight up product. So if you look at the G formula, it's a product of conditional distributions. If you look at the front door functional, there are some summations going on, but roughly it's just a product. This is one of the an interesting example where you actually get a fraction or a ratio. Okay, so the way that it will work is that okay, so I'm interested in P of YA. That's my target. P of YA happens to be equal to P of YA times P of AX divided by P of AX. You know, trivially so. So I'm just multiplying and dividing by the same thing. Okay. And then you'll notice from this graph that AX and YA are independent. Because any path from AX to YA is a bidirected path. So they're independent of each other. So I can say that this is equal to P of YA AX divided by P of AX. All right. And actually, to be a little bit more precise, since I'm going to be intervening and setting A to be equal to little a, let me also say that this isn't just any value for AX. This is the value little a. This is the value little a, so that I get little a everywhere over here. So now let's just focus on the denominator for a second. So the denominator, as it can be identified as follows, as Thomas pointed out, ZXA is the front door graph. So if I want the effect of X on A, I basically am saying, you know, I can do kind of a replacement. I have A to M to Y. And in this case, Z is playing the role of A, X is playing the role of M, and A is playing the role of Y. And so this is just given by the front door formula. So this denominator is equal to a summation over Z, P of Z, P of A, given X and Z. That's front door with some relabeling. The numerator is essentially the joint effect of X on A and Y. And it's basically the same as this, except I have P of Z times P of A and Y given X and Z. Let me see if I can squeeze that in. P of A and Y given X and Z. So it's exactly the same as the denominator, except you also have Y being a random variable in the numerator. And that's the identifying functional. This is the effect of A on Y in the napkin graph is identified by this ratio. I believe there's estimation work going on this, but ratios are tricky. But sometimes ratios also license you to do clever things like targeting the ratio itself rather than estimating the individual densities.
Sorry, Rohit.
Yeah.
I'm confused about the denominator. Is that P of AX equals 0?
Sorry, these should all be a equals little a. And say that one more time, Caleb. Is it a?
The underlying guy in the denominator, is that P of AX equals 0 or P of A equals 0? To the left.
This is a equals a given x and z. Right?
The thing on the left of that.
This is ax equals little a. I'm sorry.
AX equals little a. So this is like effective x on a?
Effective x on a.
Okay.
Yeah.
So I'm confused about how that relates to the front door then, because is that not effective z on a?
Can I ask something?
Oh. Yeah, go ahead. One sec.
Is A a mediator variable? And what is confounding variable over? What is the set of Z?
A is the treatment over here. It happens to be
X is not treatment? X is not treatment.
No, x is not treatment in this graph. No. X is just a variable that you have lying around that happens to satisfy these assumptions. It's some pre-treatment variable. Yeah, but let me go back to Caleb's question. It's a good question. I'm confused. Let me stare at this for a sec. Okay, so P of AX equals A. I intervene, and I'm marshalling. Oh yeah. I'm sorry. So so this is the effect of
This
M.
is just backdoor.
Yeah. It's backdoor in the front door graph to get the effect of M on Y.
But if you wanted to get really fancy, you could do front door in the front door graph and then magnify it that way. You get something horrible which is equal to that.
Yes, correct. Yeah, I misspoke. Yeah. So this is, but you are estimating, you are deriving the effect of x on A, which in this case is, just given by backdoor, basically. Okay. Yeah. Okay. So that's the final functional. There's some interesting work going on. I think Razia Nabi and her student Anna Gore working on it. I've maybe heard rumblings about Andrea Rudnitsky working on this. I'd be excited to see some nice estimators for this functional. And also applications of this functional. I do feel front door is now having its moment in the sun. I think, was it at IJE, International Journal of Epidemiology, it just won, a front door paper won the best paper award. And I think people have recognized that maybe front door is nice for vaccine studies. So you have A to M to Y, and A is your vaccine. M could be the marker, like T cell count, that shows whether your vaccine is effective or not. And so that's a good mediator. And depending on what you believe about that T cell count, maybe if you condition on a sufficient number of covariates, you get that there's no unmeasured confounding involved. Okay, so I won't go through the proof of this. I'll go through this relatively quickly, but I do think this is a very interesting result. Also has nice connections with the linear SEM literature, so linear structural equation models. So you could ask. We've talked about when the full data law is not ID. So we've talked about cross-wall parameters not being ID. We've talked about when the joint post-intervention distribution could be not ID. And we've talked a little bit about when things like P of YA could be not ID. You could also ask, when is a one-step ahead potential outcome not ID? So we know that the model is defined in terms of these one-step ahead potential outcomes. When is it impossible to identify non-parametrically a one-step ahead? Ilya in his thesis and Matthias Durkin, Feugl, and Sullivan So Ilya proves it for, he uses a binary model to make his point. This paper uses a linear SEM, but it turns out the criterion is the same for both. So one step ahead potential outcome is ID if and only if there is no C tree that is rooted at VI in G. So C stands for confounding, tree stands for tree. So here's when you get a VI rooted C tree in G. So this was the napkin graph, right? So I had Z to X to A to Y, and I had Z bidirected Y and Z bidirected A. So let's focus on Y. So we have a C tree that's rooted at Y. If you have this entire graph being a single bidirected component, so you have every variable somehow pathwise connected via bidirected edges, and then all vertices in G have to have a single directed path to Y. So the second criterion is satisfied in this graph. So I have Z that has just a single directed path to Y, X only has one directed path to Y, so does A. But the entire graph is not bidirected connected, a single bidirected connected component. That would happen if, for example, I add X bidirected Y. So you'll notice that there are no unmeasured confounding edges between A and Y at all. Yeah, question.
I'm so sorry to be pedantic. C tree of size more than 1.
Yes, C tree of size more than 1 because a bow arc is a C tree.
Well, a single variable is a C tree.
Oh, a single variable is a C tree. Sure. Yes. Yeah. Okay. Bow arc is C tree size 2.
Yes.
Okay.
2 would work. 1 would not work.
Yeah. Okay. So this is a C tree because we have this bidirected path from every variable to every other variable. And the interesting thing about this is that you have no direct unmeasured confounding between A and Y, but it turns out that since YA is a one step ahead potential outcome in this graph, you actually do not get PYA. So you have this Y-rooted C tree in this graph. It turns out you get all of the other one step aheads because, again, if you just ignore Y, you have the front door graph on Z, X, and A. I think is kind of neat. All right, I will skip over this. This is again, a lot of parameter counts, and we'll go straight to Verma constraints. Okay, so Verma constraints basically one interesting way in which they emerge is that you look at a graph, and usually when there are missing edges between two variables, you ask. You try and use M separation to determine whether there's a constraint between them. So there's two missing edges here. There's no edge between Z and M. So in this case, it turns out that if I just apply M separation, I get that Z is independent of M given A. So that's a regular conditional independence. However, if I think about the missing edge between Z and Y, so I've drawn it dotted over here, as it's not present, we're just debating about whether it implies a constraint or not. I could first ask, is Z independent of Y, just marginally? The answer to that is no, because I have a directed path from Z to Y, so I don't have marginal independence between them. So I say, okay, let me try and block that path. So I ask, is Z independent of Y given A? It turns out no, because I blocked the directed path, but I opened this collider. So I have a colliding path Z to A to Y. So it turns out that this is not true, and this is not true. I can ask, is Z independent of Y given M, so that I don't open that collider, potentially. Turns out that's not true, because conditioning on the descendant of a collider also opens the collider. So this one's tricky. This is not true either. And then finally, of course, Z is not independent of Y given A and M, because you just open the collider. Okay. There is no ordinary conditional independence constraint in this model, despite there being a missing edge between these two variables. And Jamie, actually in his 1986 paper, points out that, in fact, there is an equality restriction. In particular, in causal terms, it says that there's no direct effect of z on y. The effect of z on y is mediated entirely through a or equivalently through m, however you wish to look at it. And so you can say, okay, like what is the post-intervention distribution where I intervene on m? So if I intervene on m, if you go through the identification, this is the form of the post-intervention distribution. So it's basically, if I just look at the natural factorization of this graph, that's p of z times p of a given z times p of m given a and z times p of y given a, m, and z. So if you think about intervening on z and m, it's basically dropping these two terms. That's the G formula, and then you end up with p of a given z and y given z, a and m, and then you marginalize over a to get the effect of m on y. Okay, so what Jamie and Larry Wasserman pointed out in 1997 is that if you apply this natural parameterization of this graph, where you just do conditional distributions of each variable given the preceding variables, and you try and look for constraints, maybe you score it using the Bayesian information criterion, you will not find any constraints, except for the regular conditional independence of z independent of m given a. What they said you should do is, well, actually, before I go there, what you could do, however, is you could use the Mobius parameterization of this graph. That captures all equality restrictions, and you can use that, use the BIC score and sort of adjudicate as to whether there should be a z to y edge or not. Now, that requires you to specify a fully parametric model because you have to assume everything is binary or discrete. You could also do this with linear SEMs if you want, so you would then specify a multivariate Gaussian. But a more general way of doing this is to do sort of an MSM-style conditional independence test. So in MSM, you do some sort of reweighted regression. So in this case, you could also do a reweighted regression to do this conditional independence test. And with the 5 minutes I have remaining, I will just quickly show you what that looks like. Okay, so I'm going to generate data from this DAG. So I've replaced the bidirected edge with an unmeasured variable u. But otherwise, it's the exact same ADMG that I showed you. I'm going to produce a ton of data from this model, and then I'm going to do two things. The first thing I'm going to do is that I will fit a regression of y as a function of z, and show you that there's no constraint between y and z in this model if I just fit an ordinary regression. So this is just an ordinary least squares model that I'm fitting. And then the second thing I'll do is I will fit a model for P of m given a. So if you think about IPW weights, for if you were to intervene on m, the IPW weights might look like m given a, or m given a and z. And then what I'll do is I'll fit the same regression, but this time using weights. So I will provide the model the weights 1 over P of ma. So it's a reweighted regression. And so then if I run that, what you'll see is that if I apply no reweighting, the coefficient for z is pretty large, like large in the grand scheme of things, it's 0.4. And then if I apply reweighting and do this reweighted regression, you get something quite close to 0. And so that corresponds to this Verma constraint. So they're independencies in a reweighted distribution, or a post-intervention distribution that you can arrive at using reweighting. And then, of course, you can construct your confidence intervals for this and get some sort of uncertainty about that coefficient. Okay, so just quick summary and key takeaways. Mixing potential outcomes and graphs has made identification a lot clearer, I think. With SWIGs and maybe not everyone is sold on the graphical framework, but it's certainly brought a lot more people on board by doing this sort of blending of these two frameworks. And I think doing this for non-identification proofs may make them stronger as well and get more people on board with why non-identification is important. Just going back to that decofounder quote, maybe they won't think of these examples as so pathological if we're able to show them a whole class of examples that are non-ID. There are equality restrictions in hidden variable graphs that are not ordinary conditional independencies. And I think reliable finite sample testing and using these restrictions in effect estimation are sort of open problems. Okay, I have 2 minutes, but I'll end there. Thank you. Yeah, go ahead.
I mean, sorry, I'm not part of this group, and then I get a little confused with this thing. I mean, this presentation was beautiful,
Thank you.
but then, but then when I think of my variables, I don't have 4 variables. I have 10 to the 10.
Yes, you can think of some of these variables as being sets of variables.
Well, I mean, that's my point. I mean, the point is I don't have 10 to the 10 variables. I have 5 fields, but they are fields. And then there's a field of U, which is either a cost or a field of V.
Yeah.
My question is, those nice arrows that you plot in there, they will convert to something much more complicated when they connect fields. Is there any generalization that can be done?
Yeah. So there. So if you assume that there's no structure among those big sets of variables.
No, there is a structure.
Okay.
With a structure.
Well, so you're always free to assume less. So if you assume there's no structure, certainly what you could do is just put it as one variable that actually corresponds to a set of variables. But if there is additional structure, I think there is interesting work by Elias Barenboim and Jin Tian on identification, where you sort of have this grouping, and then you try and you don't make the ID algorithm so fine-grained in terms of you have to specify every single variable. They kind of have clumping. I'm not super familiar with that literature, but I have seen papers on it. I think they're called cluster DAGs.
Is that 10 to the 10? I mean, I don't know.
Oh, 10 to the 10.
I still have 10 to the 10, but 10 to the 10 numbers.
Well, I see with 10 to the 10, depending on your sample size,
no,
effect
that's
estimation.
a small sample. I mean, it's not a terrible sample. That's the air in this room.
Okay. You have like you have a ton.
I mean, it's not the atmospheric boundary layer.
Yeah.
The air in this room.
Yeah, there's also really interesting work done by Jakob Runge and his group on like climate science, and I think that kind of fits in where it's like I think they do various things to reduce the dimensionality. Like maybe sometimes you do some sort of sufficient dimension reduction, or you make some assumptions on a time series DAG in order to make it more tractable. Jakob Runge.
I think there's another question back there.
Okay.
So in that identifying functional for the napkin DAG, there was like a ratio parameter.
Yes.
I would imagine that this is an unbiased functional for the estimated point target, but your variance could potentially inflate to like extremes. So is there any discussion on what you should do in finite sample, whether it's worth taking this bias cost at like the in order to get the variance and efficiency gain, or like what are your thoughts?
Okay, that's a good question. So first I'll just say that finite sample estimation for this graph is very, very new. But I think there's a lot of lessons to be learned from IV, because IV is of course also a ratio. And I think some of the stuff that people do for variance control in IV should also apply to the napkin graph. But yeah, I mean, I think it's quite brand new in terms of like what people are doing estimation, for people doing estimation with this particular function.
Can I get the question? Who is Jakob Runge? Can you please raise your hand? No, he's not here.
I don't think Jakob is here.
You said something sitting there.
Oh no,
You're sitting there.
no, I was just
Okay.
sorry. I like pointing. But
Okay, let's pointing to the next question. Any other questions?
yeah.
Caleb.
Really interesting talk, Rohit. Earlier, I was a little surprised that you sort of hesitated to say like, oh, well, we just vary this parameter. When you're talking about non-identification, we just vary this parameter and we get, you know, I was expecting you to say, well, we could just vary this and we get full partial identification. And I was wondering why not? But I guess one of the sort of techniques you're using is like limiting yourself to a submodel and then trying to show non-identification that way. And I guess like within that submodel, that then that wouldn't work. That wouldn't give you full, you know, partial identification. Is that kind of the main limiting factor, or are there other?
Oh yeah. That's a good question. I think there's a couple of things. I think sometimes I do the submodel trick because it makes the proof easier. But even if there are ways of doing the same proofs without the submodel trick. You just have to keep track of more things, though. It's not quite as simple, because then you start to have to vary the cross-wall parameters as well. So now you kind of start to have like maybe, depending on how large the graph gets, exponentially large number of things that you can vary. But also, I guess, to me, it's not clear when you can determine whether the set of values is informative or it's just like any possible value is fine. So I think that's a little tricky. Is like when are you able to solidly determine that these bounds are informative, as even separate from like, are they sharp?
Other questions? Okay, well, we're a little over time, so let's thank Rohit.
Thank you.